Thanks everyone very much for joining, and today I'm very happy to have a talk from Dan Allan at Brookhaven National Lab, who is going to be talking to us about Tiled, which is a service for structured data access. And to many of you, Tiled isn't going to be completely new because we've been very fortunate to have Dan and some of the other Brookhaven members who work on this project be interacting with us on the Slack channel for some time now, which is great. But without any further ado, I'll go ahead and let Dan take this away and tell us all a lot more about Tiled.
Sure. So I'll share screen to PowerPoint. And unless somebody yells, I'm going to assume that this works. So we plan today as kind of a two-hander talk. I have previously spoken in this talk series just over 2 years ago, in July 2 years ago, about Tiled in early stages, seeking feedback from some of the same people that are here today. And one of the newest developments is first-class support for awkward arrays, done in collaboration with Jim Povarsky, who is here and will show some slides of his own in the second half of the hour. Also, Dylan McReynolds, who's been probably the second highest contributor to Tiled after me, is here as well. And Dylan, you're welcome to chime in at any point. And with that, here we go. So we understand that there's a broad effort to build data services, each with their own emphasis and place in the ecosystem. And we've done all we can to understand how our own requirements fit into what everyone else is building. We learned about Service X from Gordon probably about 2.5 years ago, and have been watching that, as well as these others listed and several others not listed. This seems to be in the air. It seems to be a general need that people know that we have. When we talk about a data service, we understand we're thinking about making the data findable, perhaps slicing into it, avoiding having to download a terabyte or petabyte scale data set just to get the slice that we need. We might be thinking about getting it in a format that wasn't the format it was natively written in, but something more convenient for whatever our data analysis or visualization program is. For extra credit, it would be great if the service could help us understand what the names mean with some reference to a standard, names including labels on dimensions of arrays or keys in metadata dictionaries. We want to follow the relationships between data sets, like a raw data set and a processed result, or two measurements that were performed on the same sample using different techniques. We'd like to provide open access where that makes sense, and also secure authorized access, and in general make it more practical coming from the user facilities perspective at this National Synchrotron Light Source 2 for our thousands of visiting scientists to meet the FAIR principles without spending a lot of time on their own to figure out how to do that. So the status quo in our field is really file-based data access, and file browsers that can't see inside the files, that don't know enough about the files to open them, to do partial access, not just based on byte ranges, but based on the semantics of the file, like the central frame from a tomographic reconstruction, or just a single column of a table of data, for example. That prevents barriers to the usability of these systems. For one thing, the data is often written in a format that we can't control by some vendor-provided detector, and that's not necessarily the most convenient or performant format to access the data in. I already jumped ahead and touched on partial access being important to us, and then this idea of expressing the relationships between data sets without resorting to just putting metadata in the file names, reconstruction number 1, reconstruction number 2. Finally, a lot of the formats that we deal with, even things as mainstream as TIFF, aren't supported by standard web browsers. So it makes it difficult to preview it in a lot of the web tooling that exists. And of course, search capabilities are limited if all you have is metadata in file names. In materials research, we think we have particular challenges when we compare ourselves to what we can see in astrophysics, climate science, business analytics, a lot of the drivers of data science generally. We have a large variety of shapes of data. For us, it's not mostly tabular. It's really equally tabular and image data and hierarchical structures of those. We have instruments that will generate megabytes in a day and instruments that will generate hundreds of terabytes in a day. And we have to care about all of those use cases. And we have various access patterns to that data. Our requirements are quite dynamic. We think about the James Webb Space Telescope as an example. Nobody's going to attach a new detector to the James Webb Space Telescope the morning of a measurement. There's a lot of runway to plan that kind of thing. But for us, equipment is added and removed day of the experiment, which means we have evolving formats and schema evolution that we have to deal with on a fast scale. We're also looking at a transition going on right now from traditional framing detectors that produce nice rectangular NumPy-like arrays to event-based detectors, more similar to what we see in higher energy physics, and that raises the salience of awkward array-like structures and root-like structures for us. In other domains, we think that the data structures are much more static and defined in advance. I'm sure when you get into the weeds of those, it may not be as simple as it seems from the outside, but this is how we view the particulars of our problems in materials research. So in answer to that, we've built Tiled. It's still a little less than 3 years old and still under rapid development, though it is taking shape now, I would say. We've spoken with many external groups, including this group about 2 years ago. We've focused on security from the start, and we recently passed both the routine scans you need to be on a lab network and a specific subcontracted pen test with a fully clean bill of health. So we're now soft launched on a public IP address for our staff and early friendly users. From this group, I would love to have time to hear about what opportunities we might be missing in how we frame the problem, how we understand our own requirements, what related work we should know about, maybe getting into more details of where Service X is today and how we can coordinate with other efforts, any important capabilities we're not considering, and any missed features or things that we're doing that you think we might come to regret. So a cartoonish big picture of Tiled produced by our graphics department shows that Tiled is the service in the middle, translating how data happens to be stored to how it may be accessed. That could be translating data from an HDF5 file into a PNG to display in a browser, sending it as BLOSC compressed C buffers to a Python or Julia client that's making HTTP requests to that data, or just getting a CSV from curl, a command line tool. All of these things are of interest to us. If you look at this graphic, you can spot a possible combinatorial issue here, which is that if we're storing the data in N different ways and we're supporting access in M different ways, that seems like an awful lot of code to write to translate every way it's stored to every way it may be accessed. And there have been projects that have done that, have attempted that at least, and found that it is in fact difficult. What simplifies this for Tiled is the idea that we actually don't care about that many kinds of structures. The structures we care about, striated array, table, nested structures of these, sparse array, and recently awkward, are a list that we don't think is going to grow that much. There are a couple others in the wings, maybe histograms, maybe a couple others, but that's a reasonable set. And so Tiled will read data from a range of formats into one of these structures in a lazy chunkwise way, and then export it out, serialize it into whatever format's requested. And that reduces the problem to something that is tractable. So the features of this system are structured access to data, being able to address the data set as an array, as a table, without caring about how it happens to be stored at rest, supporting transcoding and compression of the data when we access it. Even the same person might want the same data set in different formats depending on exactly what they're doing that day. Then an index on the metadata backed by a SQL database, either Postgres or SQLite, depending on what's appropriate for the use case. These things now support arbitrary JSON metadata, arbitrary JSON columns. And that's a pretty recent development, especially for SQLite. It allows us to have a strong schema for the parts of this backend that aren't going to change, but still have an open-ended area for scientifically defined metadata that can evolve however it needs to evolve without any changes to tile. And finally, we care about access control. We have thousands of users with different experiments that can't necessarily see each other's data. This distinguishes tiled from some of the use cases like czar cloud-backed access systems, where in large part you're either in or you're out. And if you're in, you can see everything. Tiled supports two modes of use. One is the one that we've been building out recently, where you upload your data into Tiled, or you register some data set with Tiled, and then Tiled is managing that for you. So that means Tiled can store the data in whatever format Tiled wants, and then it just makes it available back to the user. If you were to lose your database or the storage that Tiled is using, you would have lost your data. The other use case that's a little bit gentler, where we started, is tiled as just a passive cache that peaceably coexists with file-based workflows. So if we've got scientists who have data in a directory of TIFFs or HDF5 or CSV or whatever custom format, and they've got existing workflows that are using those file paths and relying on that data being there in a certain format, in a certain POSIX-like storage, we can aim tiled at that thing and say, we want to have service-based access to this in addition to the existing file-based access. And that means you could blow away the tiled database and reconstruct it perfectly just by rewalking those files. These two modes of use can coexist in the same tiled deployment. There's just a flag that says, is this particular asset something that tiled is managing and can update and delete? Or is this something that tiled is just indexing and passively reading? And this is kind of a bridge of trust, where we can begin by deploying the passive mode on top of existing workflows that work, but then try to move our user community to a system where they're not relying on the details of how the data is stored, not directly touching those file systems, freeing us up to experiment with more modern formats and with, say, blob storage instead of POSIX storage, by pushing our users up an abstraction layer. Tiled is not just me. Tiled is a bunch of folks at NSLS2. Tom Caswell is a name you may know as the lead developer of Matplotlib. Marcus Hanwell, Kitware, and now Voltron Data, spent a couple years at Brookhaven and gave a lot of conceptual input to this. Dylan, who's here, and former postdoc Joe Kleinhens. We initially conceived tiled as basically an intake plugin. If you're familiar with the project Intake, it's like a Python-based IO abstraction that had a little service inside there, but we found that Intake is very Python-based and didn't really have space to become a multi-language service that you could talk to reasonably from curl or from a web browser. So after a couple of years and about 45 pull requests, working with Martin Durant and Anaconda, we went our own way with tiled. And most recently, as I've said, we're looking at Awkward Array with collaborations with Jim and others. Taking a step back on how we see tiled fitting into the ecosystem. So step 0, do you even have the data, or do you have to email a PI with a nice email to get the data? Right? Having the data is better than not having the data, even if it's not particularly well labeled. So that would be step 0. Step 1, do you have some kind of database that would let you search over the data? Roughly speaking, I think this is how I would characterize Ruscio, what I think some of you know and use, where it's like a richer view of a file system that is basically files plus sidecar metadata. Tiled takes the additional step to say, we want the server to know enough about the files that it can open them and read them, describe their structure in advance to clients cheaply, and then access semantic sections of the data, more than just a byte range, more than an HTTP range request, but saying, I want the 5th frame in this image time series or something like that. here's a screenshot of tiled being used, where we're connecting to an example server over a secure HTTP connection, listing what's in there, and then accessing a slice of data, which comes across the wire as a compressed C buffer, and then drops straight into NumPy. In the bottom right, we have an example of closed source data analysis software called Igor, where a scientist has written a plugin, I guess, or macro in Igor that speaks HTTP to tiled in order to produce a search widget that shows search results in the bottom left with some metadata, and then a gallery of downsampled images on the right. What was nice about this is it demonstrates you can talk to tiled from something not Python, even though it happens to be written in Python. It's just a HTTP API that follows normal HTTP standards. And the scientist was able to pretty much figure this out. No one involved with tiled has seen the code of this plugin, but it does work. There's a React app that ships with tiled. This is really at the level of a prototype, but again, demonstrates that you can speak to the tiled server from a web application. In this case, we're looking at a frame inside a 4-dimensional array that's stored inside of a Nexus file, which is sort of a synchrotron-specific flavor of HDF5. And it's accessing a specific frame, downsampling and transcoding that frame to PNG, and shipping it to the web browser. So we're trying to meet our users where they are. We have users who would like their data in some peculiar format that just works for them based on some script that's been running forever. We don't want to be in a position of arguing with those users. We just want to translate the data into that and be done with it. But we also want to support standard formats, web-friendly formats, you might say machine learning-friendly formats, high-performance formats. Tiled gets us out of the way of having to argue about how to standardize data formats or even standardize metadata necessarily, and just get the data to the users in the form that they want it. It can be deployed at scale in scalable containers, and that's what we're doing at NSLS2, but it can also be run on a laptop. And an intended use case for this is somebody to run a little server on their own laptop so that they can write science code against tiled, against basically a NumPy or pandas or awkward abstraction, rather than leaking the details of the I/O into their data analysis code. You might likewise run it on a lab server and then have remote access to data from outside the lab securely and fairly easily, similarly to how labs will run a Jupyter Notebook server that people connect to, or a little Jupyter Hub. 3-clause BSD license, all open source. This is part of a larger multi-facility software development collaboration that we call Blue Sky, which is now also the name of a social network, but you'll see that github.com/Blue Sky is us. It's supported by a program of about 50 people at NSLS2, really only 10 of which are focused on this aspect, but that's the home of the work. And as I say, it's now on the public web, though you'd need a BNL account to log in. And we are seeing this as a long-term solution that tiled or something like it is something we'll support for a long time. So again, my feedback slide, I can take a couple minutes to show something interactive, to show a little demo if that's interesting, and then hand off to Jim. But for the moment, I'll take any questions.
Yeah, I think we'd definitely be interested in seeing a demo, but as you said, let's take a few questions. So I see Gordon has his hand raised.
Actually, my question was about was the demo something that Jim was going to do? So he's going to show off awkward with tiled. Is that?
I think I'm going to do a little demo, and then Jim may do a little demo.
Yeah, we
Okay.
both can.
All right.
Especially-
Okay, great. I just wanted to make sure I was going to see something that involved, or I was going to ask if it was possible to see something involving awkward and tiled, but
Yeah.
that sounds like that's covered. So
Yeah.
that was my question.
No, I think that's important to cover. So thanks.
Chiming in on top of that, with respect to the changes in the ecosystem that we've had for building task graphs and stuff like that, and having delayed access to our data, do we have the demo with Dask awkward as well?
There is no support for Dask awkward in tiled, but I think that's a pretty short step from what.
Yeah, I think I agree with that. So okay, all right.
Yeah, we are using. I think you may know this, but for everyone, there's something called type tracer in awkward that's used to compute what parts of the underlying data store are actually being used by a given slice. And that component is also now reused by the tiled client. So we're going to pre-compute what buffers specifically do we need and only grab those buffers.
Yeah, I'm extremely familiar with that.
Got it. Was there something else?
Yeah, is that a question?
Dan Riley, do you have a question?
No, I'm unmuted by accident.
Okay.
All right, I'm going to switch into demo and make sure I leave plenty of time for Jim. So I mentioned 2 modes of access for tiled. Let me get the font size a little bumped here. Okay, somebody let me know if that's not an appropriate size. Otherwise, I'll assume things are good. So 2 modes of access in tiled. One is this passive cache. So suppose just hypothetically I had a directory with a bunch of root files in it. I'm not going to demo root examples yet because I'm not fluent in that quite yet. But I've got a CSV and some TIFFs and then a nested directory with more stuff in it and an Excel file. And that's my example of data. So I can say tiled serve directory. This is just a cute, easy entry point for tiled where you have to tell it what directory you're interested in. That's fair enough. It is creating a temporary SQLite database, and it's indexing that directory of files, looking at its metadata and its structure, and then kicking off a fast API server. So now I could come over here, and I could start IPython, for example, and I could connect to that server. And I've got a Python object that feels kind of like H5Py to use, like going through groups in an HDF5 file. That's the intent. But important difference in the data model here is this container, unlike an HDF5 group, could be millions or tens of millions of items wide. So it's making paginated HTTP requests to show the contents of this. I could list it. I can basically treat this thing like mapping, a read-only dictionary, and dig into the structure of, let me bump that font size again. Dig into the structure of this data. And so this is an array. It happens to be stored as a TIFF, but as the client, I don't have to know that. I can ask for it as a NumPy. I can ask for just a little piece of it as a NumPy array. There are other types of data in here. We had tables. I think that was the Excel spreadsheet. The names are suggestive that it is. And then I can go ahead and read that and get back a pandas data frame. So at the end of this, you leave tiled and you're left with a completely ordinary SciPy data structure. And that's the intent. That tiled basically feels like a dictionary that stays out of your way as you navigate through this tree of data. There are also search features that I won't take the time to demo, but you can see that in the docs.
Yeah, just one quick question. So when you're descending through the square brackets, kind of going after structural data, that's for sure not reading anything more than metadata about the structure of the data that you eventually want to access.
Correct. In fact, this upfront step where it indexed the files, copied the metadata and the structural information into the SQL database. So we're not doing any IO except SQL queries in order to do this until we get into actually reading the array data.
Just had to ask out of paranoia. Thank you.
No, totally. Great question. All right, so now I'm going to do the other mode of use. That was the passive read-only mode. Now I'm going to start tiled serve catalog. And again, we're just doing a cute demo. So we're going to start a temporary catalog. This allocates an empty SQL database and a writable data directory. And I'm going to take this. This is just like when you start Jupyter Notebook, right? If you don't tell it anything else, it'll generate a random API key for you. And so we'll just paste this right into IPython, which is not good practice, but we'll serve for the moment. Okay. And if I've got NumPy, I can have a little NumPy array, and I can do C write array and give it metadata like color blue. And now my container has this thing in it. I didn't tell it what to call it, so it came up with a random key. I can grab the first thing in here and slice it and get my data back, or look at its metadata, which could be used to search. I will do a very basic awkward example. So here's an awkward array, and I will say write awkward. And I'll go and look that up. And I'll go and slice it. That might work. Nope, doesn't like that. That's probably just an illegal slice. Anyway, I'll let Jim do for real awkward examples. But what happened here on the server side is when we uploaded the data, whether it was an array or an awkward array, we first declared that there was a new data set describing for tiled its metadata, its structure, what type of structure it was, array or awkward. And then in one or more requests, in this case, just one, because it's small data, we uploaded the binary chunks of the data. In this case, the NumPy array, and in this case, the awkward array. I've demonstrated so far only that you can talk to this thing from Python. Let's quickly talk to it from curl and then hand over to Jim. So I'll upload another array. I'll drop out of IPython, but my server is still running over here. This is like curl, but it's a little more modern. I'm going to say, get me the full array that was X. And grab that API key again. There we go. Okay, so that just sent me C buffers. I could use the HTTP standard to say which format I want and say, just send me that array as JSON. And there's the array. My colors aren't great, but there's the array as JSON, for example. I could do the same thing with the awkward array, which I think we called test. And there's the awkward array. And what's really cool about this is the slicing, it just goes in the URL. So let's get me like the first item of that NumPy array as JSON, or get me the first two items. Multi-dimensional slicing works as well. So this gives a flavor of using HTTP standards to specify which part of the data set you want structurally, ignoring how it was stored, whether it was managed by tiled or came from some file that tiled just has a read-only view into, choosing your format, and applying security standards. I'll take more questions while Jim gets set up. Gordon?
I would think at this point in my career, I'd know where the unmute button was. Let's see. So I thought you had mentioned earlier, and I thought I'd seen a previous demo, that it was possible to do queries, not just on the metadata, but apply some sort of selection to the data that came down. Am I misremembering?
You can slice the data that came down for sure,
Okay.
depending on, and it depends on what the structure is, what that would mean.
Okay,
for
perfect.
tables, you're selecting on columns and partitions. For arrays, you're doing n-dimensional slicing, so on down the line. You cannot currently query a data set, like filter which data sets you want to see based on things that are in the data, because that would then require us to like open and read every file. So the thing I would recommend is lift that derived number up into your metadata dictionary and then call it.
Right. Okay. Perfect.
If it wasn't clear, I see Lindsay, but if it wasn't clear, the data model of tiled is that everything in tiled is this big tree that's then addressed by the segments of the path in the URL. Every node in that tree has one of those structure families that I put up on the slide. And the node also carries a sidecar JSON metadata. So you've always got NumPy array plus JSON metadata, or awkward array plus JSON metadata.
Right. But my impression is that you do open all of these files. It's not that, it's just that you don't want to spend the CPU time or the design, because you'll move from format to format, which means you must be opening the files.
Once you're accessing the data, we're opening the files. But if we're doing a search query and just listing, which items out of these millions match a condition.
No, I guess I meant like once I have a data set, I only want the NumPy rows that have a number greater than 100 in them.
Oh, I get it. You want to do like Boolean masking on the NumPy array.
Right, or something like that.
I wouldn't rule it out, but we don't support it today.
Okay, perfect. Thank you.
Lindsay?
Cool. Yeah, I was wondering if having a sort of mixed mode of an augmentable data store that's originally indexed by a file is something that you have in your roadmap, where you have some set of data that's produced by your experiment, but you're going to add some doodads to it afterwards. And that would need the extended functionality or the write back functionality that you just showed us, but it's all going to be keyed by the same underlying, run number or whatever.
Yes, that makes complete sense.
Yeah.
Keep going though. Yeah. Mm-hmm.
So yeah, this is something that we're intensely looking for in high energy physics, especially with like object stores and things like that. And I was just wondering from y'all's perspective if you're thinking about doing something like that. And then there was a secondary question related to, and I think you mentioned something on this earlier, related to what the database that is indexing all your data can be, and how that can be backed. Like, can it be Ceph? I guess the data store would be Ceph, but then you can imagine indexing it to meet the scale of the data that you're trying to use tiled with and things like that. And it would just be nice to understand what sort of options are available for backends.
Yeah. Let me address the first question first. The logical view of the data, the logical view of those nodes in a tree has one table, and then that has a one-to-many relation with its backing data sources. And so a use case of very strong interest to us, we need this already, is having one logical table where some of the columns come from, say, Arrow, and some of the columns come from HDF5, where basically some of these columns are being written by a detector in a workflow that we don't control, and some of them are being written by us. And we want these to be seamlessly part of the same data set from the point of view of the user. Yep. Okay. Now yours was a little different in that seems like there's a large passage of time between the creation of the first data source and the creation of the second. But I don't see an architectural issue there.
Okay, got it. And it seems like it's necessary, so it has a high probability of happening. Cool.
Yes. We've laid track for it, but I don't have like tests that test it yet. Gotcha. The second part of your question was about the backing store. Just to clarify, is that the backing store for the data or the backing store for the SQL database, or both?
Both.
Okay. The tiled server has a pluggable adapter backend where you could run tiled without these databases at all. You can just say run a tiled server on top of basically this NumPy array or this dictionary of various objects. And that's the first thing we wrote. So the server and all the auth logic and all the transcoding stuff can run completely separately of this idea of a catalog or a database of metadata. And so if you wanted to do something really different, you could reuse that piece of tiled and say, we're dropping the SQL stuff in the ocean and we're doing our own thing. We actually have a Mongo version of this that's not in tiled main, but it's like an experimental adapter that plugs in. So there's evidence that you can really do radically different backends for tiled. For your use case, I think the SQL can get us pretty far. I mean, Postgres and SQLite are nice, boring, scalable.
Yeah, for the metadata, it's not
right?
too bad. It's just thinking forward to like HLL8C, where it's or that would be over like a petabyte of active analysis data or so, where I see possible scaling problems on even the metadata.
Yeah, so I think we're looking at custom adapters for the data and maybe something experimental for the metadata as well.
Okay, but that's also, you know, end of life HLL8C kind of stuff. So we have a while to solve that problem.
Cool. Should we hand it to Jim?
I can check this screen sharing. Sure. So now you see my slides?
Yep.
All right. So yeah, so I'm going to follow up with ways that we can use it. I'm going to start talking about root files. So just some facts about root files. So this is a root file. It starts with a T file header, and it's got T directories and all these things in it, and all of this is one single file. And when we want to get what we consider the data, the T tree data or the Rn tuple data, it's all in these T baskets. That's just how it's granular structured. But finding where the T baskets are within the file involves quite a few hops. Let's say that you already know, just at the beginning of the process, that you're just going to want to read all of the branches as arrays, or the specific set of branches as arrays. In order to do that, what root or uproot needs to do is open the file, find a pointer to the root to T directory, find the pointer to its list of keys, find a pointer to its T tree, and this has an array of pointers to all of the T baskets that are relevant for this. So if this is a remote file, that's a lot of round trips. You can't do the next step until you get the response from the previous step. So that can be a latency problem. We kind of like to have a database of T-basket positions and sizes so that we could just jump right to that. So that's where I'm going with this. So this would be like an application on top of tiled, where tiled would be that database. So why would you want to do that? Well, one is replace the latency of 4 round trips with the latency of a database, and maybe that database is more nearby than the file itself. This is a specialized T tree and Rn tuple access. Rn tuples work this way, but they're called R blobs instead of T baskets. Same for round trips to get to the starting point. And of course, the reason that root is structured this way is so that root can have histograms and all sorts of other different kinds of things. This would be a specialized kind of access for only T trees or Rn tuples. And then an alternative to this is to convert all the data from root into some other format that doesn't have these multiple steps. But as Dan mentioned earlier, there are reasons to leave a set of root files in place so that traditional workflows can continue to run against them. And then we just gain this additional way of accessing it. And then if we've got a tiled database of awkward arrays for like user-derived data that users can write to, this can be made to look the same way, so that when a user is asking for data, some of the data might come from root files that were produced essentially by the experiment, and also user-contributed awkward arrays. This is not a new idea by any stretch. Nick has been talking about this for years. The biggest talk on this, from what I found, was this one on metadata thoughts and some coffee tools, where he's describing a column service that, well, essentially does what I said, but is different architecture from tiled, but serving the same purpose. And then showing the need of it, Nick did some performance tests where this is a known fact in coffee analyses, that getting the metadata is itself a significant step. So if we could just like have that metadata served up by a database, that could be quicker. Yeah, so even just getting the branch names can be significant. So if we just had those to start with, it'd be better. Now, root metadata is awkward in the capital A sense. It is large and complex structured. So I picked a typical root file. I just went into CMS data and got a file, and I hope it's representative. Most files are hovering around the 2 GB mark. This is typical of that. If you were to uncompress it, it would represent 13 GB of data. It has thousands of branches. Most of them are triggers. Only like 400 of them are not trigger lines, because in CMS Nano AOD, each trigger is a array of Booleans. And then this comes out to being 500,000 T-baskets for one file. And it's even just 250,000 for the non-triggers, so that's pretty significant stuff. And then if you were to go and add up all of the compressed data among all those T-baskets, you get almost the same, almost all of the data really is data. But it's just broken down into these baskets that are quite small, about 3 kilobytes for the triggers and 9 kilobytes for the non-triggers. So if we were to turn this into awkward metadata, I'll be showing on subsequent slides, this represents 14 megabytes of metadata describing this 2 GB file, which you can compress down smaller. That makes it less immediately accessible. And this is pretty consistent because, if I compress this awkward metadata down, I can get maybe 4.9 megabytes without trying too hard, just using gzip out of the box. And root out of the box was 5.1, and root is storing more than what I'm storing, so that makes sense. It's most of the metadata is positions of baskets. So a conclusion from this: the uncompressed metadata is about, almost 1% as large as the data itself. So if you had, several terabyte data sets like the double muon in the public data, you've got some thousands of files, and you'll have, tens of gigabytes of metadata in this database. So you need a significant database. Oh, in terms of prior art, what we're doing is also what a project called Kerchunk does. When we were first talking with Martin, Kerchunk stored everything in JSON files, and I said, well, that won't work because of the size of this. But since then, Kerchunk does Parquet also. So what does the metadata look like? Well, this is actually a first draft. What metadata would I build in order to know everything that we need to know about a root file in order to more quickly access it? So this is going to be a set of root files, actually. So you have a list of files, each of which has a file name. It has a list of branches And for each branch, we're going to need to know the seek position in the file, which really has to be 64 bits, an entry stop, and a number of bytes. These could be smaller. We could make them 32 bits. That's what we need to know for every branch. This is a list within the file. So it's a list of lists because you have files and you have a list of files and a list of baskets inside the files. And then trying to do a bit more optimization here to take part of the file name and put it in a prefix because many of them are very similar. We're going to need the interpretations in order to, the uproot interpretations in order to turn these bytes into arrays. That has to be stored somewhere, and a set of root files can vary. You can have small differences in the data types. So, but they usually don't. So I, pulled that out into like an era is describing the tree name, the names of all the branches, and their interpretations, and then a single file would just reference one of these eras, and you should not have very many eras, just as you have not too many prefixes. And then on top of that, a global entry numbers go to, which file. So if you want to get, entry 1 billion to 1,000,010, which file do you look at? You want to be able to jump to that very quickly. So we have these offsets. Oh, and I explained all that. Okay, this is for after the fact. And this is a perfect match for Tiled's slice-based predicate pushdown. It was really able to use the fact that Tiled does slices on the server to minimize the requests for metadata. So we don't have to ask for this 41 gigabytes of metadata when we want to do a particular, satisfy a particular request. So here, put into an awkward client and do a slice on the server asking for the offsets. This is just one file, so the offsets is just 2 values. Fence post principal. Ask for the prefix, ask for the file name with its prefix and era number. And now let's get some fancy slices, like go into the branch names, and let's pull just 3 of the 1,400 branches, and muon, muon PT, and muon eta, and get their seek, stop, and bytes positions. Or go even deeper than that and only select some of these, do a slice of just a few of the baskets. This is put into a new project that, whether this will be a separate repo or will get absorbed into Tiled is up in the air. But let's call it a prototype for now. So what this prototype does is it populates the Tiled database. You look at some files and populate the database with all the metadata that you need, and then it acts as an uproot drop-in replacement. So having populated it, you can ask for a tree, and let me put that in quotes, is actually a tiled uproot object. But it has the same methods as a tree. You can do the show method, and we'll be asking for arrays in a second, because it's actually subclassing classes from uproot. So it's uproot doing this. You can ask for tree.arrays and give which ones you want and which entries you want, and it will do the tiled lookups first to find out the root metadata, and then it will act as an alternate source for uproot. And once the bytes get into uproot, uproot does everything that it normally does to produce the arrays. And some of the things that uproot does is it can perform some calculations on it. This was introduced because some root files have aliases, and we wanted to be able to support those aliases. But now this is suggesting a new use for this feature. These computations of computing px, py, pz and computing a cut are being performed where this tree.arrays is. But this tree.arrays, this computation could be put into tiled as a new adapter. And so that would be this proposed structure. We have a tiled database of awkward arrays, and these have the user-derived data sets so that a client can ask for some user-derived data, which is an awkward array, and just get it. This is the normal. So that's tiled owning the data, the first of the two use cases that Dan talked about. The second is if we put this uproot adapter into tiled, if we put this tiled uproot into tiled as a new adapter with a capital A, then the client could ask for things like muon pt times cinch muon eta, and could ask for cuts to be applied. And with the cuts applied, get a smaller data set back. Now, this is something we want to think about because now this is doing some computations, but it's limited what kinds of computations it can do. For this to work, this adapter needs to have access to a set of root files and also awkward arrays and tiled. This question mark with the service X, I've been thinking about this ever since making this diagram. Service X doesn't deliver root files, it delivers columnar data. So maybe that's not the right way to do this, but we want to talk about how this lives with Service X because they are not quite the same thing. And this is my last slide. So I can take questions now in the last 10 minutes. I also left open some terminals to try an ad hoc demo, but it would be an untested demo. So let's go with questions first.
Okay, great. Okay, so thanks for both of those talks. So I'm not sure who had their hands raised first, but since Dylan McReynolds, since you're a guest, why don't we go to you first?
Okay, thanks. I was last, but my question is related to this slide right here, so thank you very much. Hey, Jim, thank you for that talk. This is really cool, and I just took a brief look at that repo. I just wanted a comment and a question that, you know, as you probably know, we've talked a lot within Tiled about this idea of how much computation do we want to, and I'll use quotes, allow, right? Because we love the idea of a separation of concerns where Tiled is just serving data and it's almost, it's like scary because you never know how big a computation people are going to need and will that negatively impact other parts of Tiled. On the other hand, there's so many use cases where we want to do this. So I wanted to see if you had, while you were thinking about this, if you had thought of what my idea is, sort of come up with the right API to make it really easy to take that out of process maybe, but still make it feel real time to the client. I'm just wondering if you'd had any thoughts on that as well.
Take it out of process. I'm not sure what.
Well, just so if you have a computation that takes X amount of processing power, put it in a different process and then come back, rather than like having those computations be in the same tiled process itself.
So that it blocks. That's
exactly.
Right.
Not blocking. And you're also not potentially running out of memory in the tiled process itself. Like if memory problem taking down tiled.
Right. Yeah. So these uproot strings already do limit the kinds of computation that can be done. So there's already a limit on that. But that doesn't explicitly limit the amount of memory that can be used.
Right.
Not explicit. Someone could write you can't write for loops. You can't write.
Right.
Can
I think this is great.
Someone
This
was
is
gonna-
this is like another use case that we have to consider about this because it comes up obviously it comes up a lot.
Yeah. Who was speaking? Was that Gordon?
That was me,
Oh,
yeah.
right.
As a direct follow-up to this, because you have this particular slide up, which, as you could probably guess, Jim, was partly the source of my question to Dylan, or the source of my question previously. From the point of view of ServiceX, the model it uses is a web API to request all the data. And the web API is not non-blocking, but it does mean that at some point you have to go check back with the service to understand if it's finished. So it takes almost no resources on the, whoever's making the request. While the request is running, it may use 1,000 cores. It may take 20 minutes, but the resource usage of the person who made the request while the request running is basically zero. I mean, just, the memory to keep around
Here,
to
the client.
understand. Yeah, and but the analysis facility, I think, which is where the tiled server is running, right?
Yeah.
Right. The client is my Jupyter notebook.
Yeah.
Right. So the Jupyter in this model here, the Jupyter notebook is not making the request to ServiceX. The Jupyter notebook goes through through the tiled server, and then the tiled server asks ServiceX for the data. At least that's my impression of what this diagram is meant to represent. So the tiled server would be the one that would be making the web requests, or a library that was imported by the tiled server or whatever.
Yeah.
Right?
Because tiled uproots first asks tiled for metadata, then
Right.
asks root files for data.
Right.
Data
Right.
data.
Right. So the key here would be that the internal tiled server is structured in a way that it's okay if the first time you request something about a data set, it's going to take a little while, right? Or the other alternative is that only predefined ServiceX data sets are allowed to be served by tiled, in which case, ServiceX can prepare the data set ahead of time and it just sits there idling, and then you can make a quick request. So one of those two models is all that would work, I would think.
That sounds right to me.
It might have.
I'm sorry?
I was just agreeing that sounds right to me. And adding asynchronous HTTP, the kind of thing where your request gets put on a queue and you get a URL, check back here later for this job, is, I think, part of the decision that we have to make that Dylan's talking about. Is that something we add to tiled, or is that a separate thing that sits alongside tiled? Right. I don't know.
Yeah. And I guess the way I was thinking of it is, you could do all of this with your own custom adapter for tiled, right? But what the question is, like, what's the right? Is there a generalizable set of features or APIs to put into tiled that would help this use case for a lot of cases?
Would tiled be comfortable with internally with a request that took, when we run on these 10 terabyte data sets, it can take 10 minutes.
Yeah,
okay.
Right now, what would happen is that the client would time out, and there would be no way for us to tell the client, no, check back, right? So we would need to both have an adapter that could deal with that,
right,
and then make it an addition to the tiled HTTP API to the
right. I was thinking, internally, you'd have to be, the coding is sometimes a little different even internally when you're dealing with something that's going to take 10 minutes, because you don't want to lock up one of your HTTP threads.
Yeah, everything's async, but I think it's a question of,
okay. If everything's already async, then inside you're probably basically set up. It's just I hadn't appreciated that, so I apologize. So it's
that's good.
the interaction with the client that would have to be changed. Okay, perfect.
I don't think we want to change tile to make it more of a processor that has to do asynchronous calculations. The thing that attracted me about it was that it's immediate. These queries, maybe I put the wrong query here. The more interesting query is doing a cut. The reason that we want to do these queries is to make the response be smaller. So this can't be a thing that takes a long time to compute. It needs to be something that takes about as much time to compute as it was to just get the data. We don't want it to be longer than that, and we want these. We want to say that we want these files to already be staged somewhere because they had to have been scanned in order to have their metadata.
Right. One very easy way to do this is, the client, at some point somebody says, these are data sets that are interesting, makes the query to service X completes, returns a GUID. Now you use the GUID as your data set name. And then everything, they're in object stores, but it's available instantly, right away. There's no lag time.
Yeah. And a thing that I forgot to put into this is that another very common case would have another layer in between here where there's Dask processors. A client starts a Dask job. So you've got this distributed job going on Dask, and each one of the Dask workers is asking for a different slice of the root data.
Yeah.
I should have drawn that as well.
Yeah, that works today with NumPy and Pandas, and honestly, I think it's really cool. The idea of a Dask task representing a chunk of an array or a partition of a table that, internally to the task, that when it computes will make an authenticated HTTP request for its chunk. When that works, it's magic. It's very cool.
Yeah. And that's
because it doesn't leak tiled to the user of Dask. The user just sees a Dask array, right?
Yeah,
so good.
That's true.
That is excellent, especially if tiled is capable of, scaling. Because here we're talking about feeding the Dask array with probably terabytes worth of chunks.
Well, one of the reasons we're very eager to make friends with you all is you have bigger data than we currently have, and so let's find those bottlenecks before while the project is still malleable.
Perfect.
Yeah,
we are more than happy to help break software.
It sounds like you have the data to do it.
Yeah, in fact, I already have because when you were putting the slices on the HTTP GET.
Oh, that's right. That's right.
Yeah.
Yep.
These awkward ones for describing one root file were big enough they had to be moved to post. So yeah, we're already seeing scaling.
Cool.
So we have a few more questions, but I see that we're already starting to run over time. So we'll go ahead and if our speakers can hang around, then let's go ahead and get these questions, though I know some people will have to drop off. Andrew,
I have plenty of time. Yep.
Okay, thank you, Dan. Very much appreciate that. Andrew, you've been very patient. Can you go ahead and ask your question now?
Certainly. So I guess this is a question for Jim. If you scroll back a couple of slides, I guess you mentioned, and I don't remember the number offhand, to the awkward definition with this one. So I imagine that it's not. Once you serialize this information, for example, for that earlier file that you pointed out, how much space does this take up? Because I think you said earlier it was something like 14 megabytes.
Yeah, if you don't compress it.
If you don't compress, okay. So the slide 6 is 14.7 megs. If you were to serialize that into binary form.
That's right. This is describing the type of an awkward array that is 14 megabytes.
Okay. Yeah, I didn't know if that also included the 14 megs also included streamer or the rest of the root metadata that you don't necessarily care about. Okay, thank you.
Right. So the streamers got turned into interpretations, Python objects for turning the bytes into arrays, and those are
Okay, so that interpretations I guess field could be quite large.
Not nearly as large as these branches.
Got you. Okay, thank you.
The branches is like 99% of the data.
Got you. Okay.
Questions are more important than me trying to do a demo. So,
yeah.
Gordon.
Well, actually, can we go to Nick because he's also
Nick is
been
next.
patiently, and then circle back to Gordon.
I don't see the list. Yeah.
Yeah, it was actually sort of coming back to a discussion about filters server side, and maybe it's worth coming back to that slide. You know, like Dylan was saying, it's a bit of a slippery slope how
Yes.
much computation you want to do.
Right.
Can you still hear me?
I can hear.
Yes.
Okay, I don't know why Zoom seems to think I'm done. Okay. Yeah, so in column service, I've decided that I don't want to be in the business of computing, because then the users get to use me to do all their work, and then they don't get billed for it. So what I figured is, well, I allow to read and write data, the client can compute it and write back their pre-computed one so that they don't have to compute it again. And I just help them along to make sure that they can use their pre-computed data alongside some other data that they decide to access later, in sort of a nice fashion. And that way the client is always, in charge of supplying heavy compute power. The only expense that you're spending there is you send more data out the first time than you might have if you computed it server side. But every subsequent access, you would still have all the benefits.
Yeah.
And so that way you don't have to take on this,
Yeah.
increased of scope, right? Essentially, of allowing arbitrary computation.
Yeah. Yeah, I recognize this as being a controversial feature. The cut is perhaps the one thing that is the most interesting and useful, although that is also a computation. I'd be happy with this, having a cutoff after 1 second, like a timeout of 1 second. If it's not done in 1 second, then it's dead.
Sometimes loading the data takes longer than 1 second.
Wow.
You're on a slope here, which is
Yeah.
which is going down fast. I think
Dylan and I had the same position as Nick right now, that we're a transfer service and slicing is important and decimation is important, where I say I want this at a lower resolution. And maybe just to add to this conversation, the first step on that slippery slope is, okay, you let me take every 10th point in this array to get a low resolution image. Won't you please just anti-alias that for me? Won't you please just do a little smoothing? That's where it begins. But yeah. Gordon, I think I stepped on you. Sorry, go ahead.
So no, it's totally perfect. And at some level, like, this muon equals 2 is just like saying something like, give me every 10th image. I mean, that's really similar. And that's why it's a kind of a slope. I mean, my general attitude, so I like Jim's idea, cut it off after a second or something like that. It's just I think you'll have a very hard time doing that. I mean, the way we sometimes just do it is, let's just do only allow extremely simple cuts. So like cut equals 2, what is it? Sorry, n muon equals 2, pt greater than 30, but never let's reconstruct the mass of the w, which involves a square root, which is hideously expensive, and then make a cut on that or something like that. So that's one possible approach.
Yeah, I think we'd really want this trigger and that trigger and that trigger and this other trigger.
Right. For skimming.
That's what we want.
Right. But that, so the other end of this if I take this to the logical conclusion, is the complete nano AOD or FISLIGHT data set. So these are sort of the analysis data sets that we have at the LHC that many of us will be using. And in Atlas, that data set size is what? It's going to be about a petabyte or something like that, I think. And in CMS, you're talking about how many hundreds of terabytes a year? I can't remember, but it's a fairly large number. Already, that might be larger than you want to deal with tiled. You may not want to skim a data set that's that size.
Mm-hmm. Yeah, we're talking about 2.5 orders of magnitude smaller than whatever it is. So a petabyte of data will need like a terabyte tiled service.
I mean, it should definitely try it to see what happens, but
yeah. I mean, with client-side caching, that might still be workable if you've got your terabyte of metadata in a local HTTP response cache, then maybe you're still running. But maybe at that point you need a different paradigm. That could well be.
Right. Which actually brings me to a technical question, which is why I raised my hand, and then I'll lower it. And it might be a question more for Jim. If I were to provide you with a function that took a GUID and returned a list of URLs to root or Parquet files, I guess root files is what you're probably most interested in here.
Mm-hmm.
What would the API of that function need to be local? Should that be an asynchronous function? Should it be a synchronous function? Tell me what you need.
At that level, the tile database still needs to be populated. So the populating the database is going to involve opening all of those root files.
Yeah, it's okay. All right, this conversation suddenly became a non-trivial answer. Okay, never mind. I'll have to do it offline.
But that'll be a long process that you do every month or whatever.
Well, I think you would just declare that the new file, whatever the ingestion process is, would right. Is what would trigger that.
Yeah. Maybe, yeah.
Yeah. So we also have a question from Lindsay.
Yeah, this is going more back into dealing with complicated predicate pushdowns and all this business. But yeah, what Nick was saying makes a lot of sense, I think, especially in the context that you guys are wanting to have some sort of augmentable data set as well. Though, and in particular, like being able, I think it would be not unreasonable if the analysis, the analysis like life cycle looked more like, okay, I'm going to, do the research and how to say it, like mapping phase of the analysis, the early data exploration stuff on the full data set that you can send me, and I'm going to be messing around with what columns I read and things like that. But then it becomes, and you get almost for free through looking at cut flows and things like that, an understanding of which cuts in your analysis are most discriminating and where you can place a mask to vastly reduce data transfer off of a given computer that's supplying data in one way or another. And this could be something in a Ceph file system or wherever. But if the workflow is like, okay, I do my exploration, I've started to lithify things, and I know I don't need to process all of this data, then it becomes critical that I can use my compute resources to construct a mask, have that mask be written back into tiled. And I think this is the workflow that Nick was thinking about. He kind of mentioned it offhand though. And then the secret trick behind all of that is making sure that we can efficiently get and this is the thing that would bring speed and not cause you to have some nasty bottlenecks, is in the machine that is bringing the data or putting the data on the network to be shipped to a given worker, it will need to be able to access efficiently the corresponding mask for that data. And we can figure out which mask to apply because that corresponds to a very specific slice of some analysis code, and we can use Dask to record that, for instance. So we know we have a way to key that specific mask for our analysis. Would there be a way to make it so that essentially written back masks like this on the rows of the data that we want to read can be made cache coherent, so that we don't have to spend time waiting for the mask when we do our subsequent runs of the data to get that on the processor to do the masking to finally send the data off to worker nodes to do further analysis? This, I think, starts to create a reasonable workflow, and that reasonable workflow has a reasonable division of labor behind it. Because the only thing that this would mean that the only thing that you're allowed to have as a predicate pushdown is essentially access, like if it's going to be a mask, is access to data that you have already pre-computed and put back into your database. And then you just have to make sure that access to that pre-computed data remains efficient when you're trying to stream outside of your storage network. Sorry, I was putting that together as I was talking a little bit, but did that make sense? And do you think this is somewhat possible? And Nick, is this kind of what you were thinking, that you have kind of this looping cycle of building up your analysis and efficient data workflows within it?
Sorry, I was heating up some lunch, but yes, in column service, that was basically what I cobbled together and said, okay, you can either store derived data, you can store a mask that you can reference to dynamically generate the derived data, even server side. Yeah, so like this would be an extension, right? You know, instead of saying, oh, I'm going to decimate, I'm going to refer to this pre-computed other column that is just a bunch of Booleans.
Yeah, we have very particular opinions about how we decimate, I think is the right way to characterize it.
I feel like this question came up for us too. Sorry, not to derail, just to add, I think this use case came up for us about 2 years ago, and again for me last week, of somebody asking about masking server side in a non-trivial way. But keep going about how that worked in column service, Nick. I'm curious.
Yeah, so I think.
Or there he is. He's back now.
So yeah, no, it was just as simple as the client sends back a Boolean array, and then it can reference it later and apply it also to other columns that it didn't originally read, right? So you could maybe read one whole column, compute the Boolean array on your side, send back that array, and now you use that to slice another column that has the same original compatible dimensions. And then optionally, you know, maybe cache that sliced array.
Oh, what if that's a new adapter, a Boolean slice adapter? So suppose that you've got, you know, all on the server side, you've got some process that can ask tiled for arrays, you know, for slices of arrays, and it can ask for multiple. It can ask for a base array and a Boolean array, asking for both of them for the same slice. It applies the Boolean slice and sends that out. So just as this is acting as a go-between, where client or Dask worker asks this for some slice, and it uses other data in order to produce that and send it out. Suppose that that's just another node type, another adapter type. Is Matt doing questions? I can't see everybody at once. I see Dylan has a hand up.
Well, I was going to say we've had discussions recently similar to that, where we keep tiled as a data service really, but take those post compute slices, put them back in tiled, and then they're much quicker to get the second time. And so if
Thinking through one,
it could be an entirely back-end process that does that as well, not the client if you want. But it turns tiled into sort of not really a caching service, but you can certainly link from like your original data set to that small post-process slice with tiled metadata so that you know you can get to it after it's been created.
To iterate on this line of thought a little bit, so currently you can slice by giving a numpy style. If we just think about arrays and awkward arrays, they take a slice query parameter that takes a numpy style slice string and applies it. And that happens above the adapter. That happens in the tiled server, so that if the data came from TIFF, the data came from awkward, wherever the data came from, you don't have to re-implement the slicing logic n times. It just happens in the server. I could imagine adding a second query parameter that is mask, that takes a URL to a tiled data set, which itself may be sliced, and then likewise is handled in the server so that you don't have to do it in every adapter. My main concern about that would be the general concern about doing expensive compute inside a server. But it might be okay.
But the compute is just Boolean slice. That is the compute.
Yeah, that's true. And if it got pushed down, I mean, HDF5 doesn't let you do fancy slicing, but it sounds like Uproot does. So
I think I'm a really big fan of do it in the adapter and then come up with all the things that make your stuff useful, and then look at what the adapters are actually doing and see if there's a way of generalizing that.
That seems reasonable enough. You do need to expose something to the client so it can say what mask it wants.
Oh, true.
Right. No, I was thinking about this being a new, a new green box, so that it can be used for uproot, or for awkward arrays, or for numpy arrays.
Yeah.
That's probably it. Or for the tables, data frame like objects. You would want to apply a Boolean slice equally to every column.
Yeah. That's interesting.
Okay, so it seems like this has been an incredibly productive meeting, given that we've had quite a extensive discussion. So I want to thank everyone very much for thank our speakers for some excellent talks, as well as thank everyone for their engagement. I'm sure that this is going to trigger lots of follow-up on the IRIS-HEP Slack, which I hope Dan and others will be involved in. It seems like there's also continuing ideas here, so I'd very much encourage people to follow up independently. And while Jim did have some, untested live demos ready to go, since we're now 20 minutes past the hour, I think we'll probably shelve those until they become more mature tested demos. Okay, thanks everyone very much, and we'll have our next IRIS-HEP topical meeting for those who are interested on Monday, October 30th. So hope to see you there.